Okay, guys, we at this point for two-dimensional motion have talked about vectors and how we use vectors to solve for whatever we're looking for. It could be distance, it could be velocity, it could be force, okay? And we've also talked about two-dimensional motion. That could be projectile motion, a projectile off a cliff or from a bridge. Okay, we talked about that. The last problems that we worked, which we're going to go over again after I get back in the classroom on Tuesday. There's also projectile motion like a cannon being fired, okay? And we use vectors to solve for different things. So also in two-dimensional motion, what we haven't talked about is motion in a circle. This would be like you're holding a string with something on the end, like your keys. You're holding your key lariat between classes, and you're walking down the hall and you're twirling your keys around and around, okay? Your keys have circular motion, but it is motion in two directions, in two dimensions, okay? So today's notes are going to talk about this motion. So, tangential and centripetal motion. First slide. We need to get some vocab, and when I get back in the classroom, I'm going to be going over this in great detail on the board. But for today, make sure that you get the notes down for the equations and the definitions. So when we talk about it in class or in a future video, you actually know what I'm talking about. So, the relationships between angular and linear motion. So, we have an object. You're twirling your keys. And assume that was a perfect circle. Okay, here's your hand holding your lariat, and your keys are going around and around. Your lariat is the force that's keeping it in an orbit or in a circular motion. Okay? And the object, in this case, your keys, have a circular motion and have a tangential speed. So there is a force, your lariat, that's holding the keys from going flying off. Okay? At the same time, Newton's laws, let me see if I can get this in focus here. Newton's laws are saying any object in motion will stay in motion unless acted on by another force. So it's wanting to fly off this way. But your keys can't. They can only follow this path because of the lariat that's holding them. Okay? So there's one force here, and there's a force here. The inertia. The inertia is wanting to make the keys go in a straight path. But it can't because this is holding it back. If you were to draw a line tangential, or it could be there, it could be there, a line that touches the arc of the circle, okay, that's a tangential line, it has a speed. Okay, so how fast these keys are going around at any point is the tangential speed, the instantaneous linear speed of an object directed along the tangent of an object's circular path. Yes, that is a mouthful, but what it is, it's the speed at any point along the key's path. Okay? It's as if you're calculating speed of a car going down the road. It's going in a straight line. Okay? You can draw straight lines at any point along the circle, and it's the speed the keys are going at that exact moment. as it goes around the arc. Measured in meters per second, just like velocity, okay? Tangential speed is the radius times the angular speed. So it's VT, R, and the angular speed symbol, which is right there, that little funny looking W. Okay. So the velocity tangential, the tangential speed, okay, we're going to call that VT, is equal to the radius of your circle times how fast it's going around. How fast are those keys going around in a circle? And it's that symbol. Okay. I realize this is upside down for you, but I cannot write upside down. And I don't have a dot cam here to flip it for you. I'm using my regular webcam. Okay, so tangential speed, here's how you calculate it. It's the speed of the object at any point along the path, the circular path. Next slide. There's only like 4 slides, so. Tangential acceleration, the instantaneous linear acceleration of an object in the path of the circle. So, let's say there's keys, you're going to start twirling them faster and faster and faster and faster. The rate in which they increase in velocity or speed is your tangential acceleration. Just like regular acceleration, it is measured in meters per second squared. Okay? To calculate how fast this acceleration is, we're going to use acceleration tangential, so it's how fast your keys are speeding up as you twirl them faster and faster. It's going to equal the radius, because you consider radius as your distance. It's your radius times your angular acceleration, and that is this sign here. Okay, so this is angular acceleration, and what angular acceleration is if I were to draw a line here, okay, the angular, how fast is this angular, this angle increasing, okay? So how fast is basically the lariat changing angles? How fast are you twirling it? Okay, it's another way of looking at what this is. What is the acceleration of the lariat as you start going slow and then you start twirling your keys faster and faster? Okay, I'm going to go back in the slide because I forgot to. Likewise, this angular speed here, when you're calculating the velocity, okay, it is the velocity in which the lariat is going around or the string is going around. That is your angular speed, okay? I should have mentioned that before. Okay. There's a thing called centripetal acceleration, okay? It's the linear acceleration directed towards the center as a circular path. So we've been talking about the tangential is the object here. It's how fast is it going around? What's the speed? What's the acceleration of the object as it twirls around? Now, the centripetal acceleration, okay, so acceleration centripetal is the linear acceleration directed towards the center. So it's the acceleration of the actual string. Okay, so you start twirling slow with the lariat. Depending on how fast you're twirling your lariat, your string or your lariat's going to go fast or faster. Okay, whatever that speed is of the string, the rope, the lariat, whatever you want it to be, it is the acceleration of this component, of this dimension. It is calculated by the tangential speed squared, the tangential speed squared, okay, divided by the radius. Okay, the radius from the center to your arc. Or another way it could be written is the radius times your angular speed squared. Because we already had this one of the other equations, and we can substitute it in. So it's either the radius, the tangential speed squared divided by the radius, or you can use the radius times the angular speed squared. Okay. Don't get upset and hyper about these abbreviations. Okay. I am not going to have you memorize what everything is. You're going to have the equations. You're going to have your notes for the test and when we start calculating all this. So don't panic. I just need you to know that if it's a tangential velocity or a tangential acceleration, it would be the acceleration or the velocity of the keys in this example. The centripetal acceleration is the acceleration of the lariat or the rope or whatever you're twirling. Okay. If this were a road, okay, you've all gone around a curve and you have felt as you go across, let's say you're going on a motorcycle or car, okay, you have felt this force of your bike or your car. It's if it wants to go straight, but the tires are making him go along the curve. It's the same difference. This acceleration to the inside of the curve, this acceleration would be your centripetal acceleration. How fast your car is actually going around the curve, the acceleration or the velocity would be your tangential. Okay. And then we have tangential and centripetal accelerations are perpendicular. So if this is my tangential acceleration, perpendicular to that is going to be my centripetal acceleration. Because they are perpendicular, we will be able to use the Pythagorean theorem just like vectors. In fact, they are vectors. We'll be able to use the vectors that we know and how to solve for those in Pythagorean to solve for these problems. And that's what we'll be doing this week. Okay, for my in-class people, my face-to-face, get these notes written in your journal. You can show them to me tomorrow, Tuesday when I'm back in class, or you can submit them online. For my remote learners, please get these in your journal, take a picture and submit them. Before I assign the calculating centripetal and tangential velocities and accelerations, there will be a video in which I step you through some sample problems until you feel more comfortable on how to do this. Okay, good night, guys, and I look forward to seeing y'all when I get back.